Let's tackle 10.34. This problem gives us three molecules or ions and asks us to predict the molecular shape, the electron group geometry around the central atom, and also the perfect bond angles for that particular structure. Okay, so let's get into this. This is a really nice problem. It's representative of the type of thing that you should be able to do if you've mastered the concepts here in Chapter 10. The first molecule of interest is O3. This is three atoms of oxygen bonded together, also known as ozone. Okay, so whenever you're trying to predict either the electron group geometry around a central atom or the molecular shape, you need to start by writing the Lewis dot structures. Now, this was not explicitly asked for the problem, but it's required to solve the problem successfully. So I've added another column for Lewis dot structure in each case. Now, in the case of oxygen, you know that we've got three atoms of oxygen bonded together. If you look on the periodic table, maybe you've even committed this to memory by now, you know that oxygen, each copy's got 6 valence electrons. So we've got 18 valence electrons to build our molecule with. So we start with the central oxygen atom, connect it to the others via chemical bonds, and we start completing the octets such that 18 electrons are used. Now, if I do non-bonding pairs everywhere, or lone pairs everywhere, I've got 6, 8, 10, 6 more, that's 16, plus these, which makes 20. This structure is used 20 electrons. I've only had 18. That's not allowed. I need to share more. Now, I can do that pretty easily if I erase these and these, and just make a double bond on one side of the central atom. Now this one's got 2, 4, 6, 8 associated with it. Its octets complete. The central oxygen's got 2, 4, 6 bonding electrons that are shared, plus these two, that makes 8. Its octet's complete. And I've got 6 here, plus these two, its octet's complete. I've used 2, 4, 6, 8, 10, 12, 14, 16, 18. The structure uses 18. I've had 18 to use, so it's a valid Lewis structure. And of course, I could shift the double bond over here, write a different resonance form if you like. No big deal, okay? But you get the idea. This is our Lewis dot structure for ozone. Now, how can we go about predicting the molecular shape and the electron group geometry? The Vesper theory tells us to consider the central atom. And when we're applying the Vesper theory, we consider the geometry around that central atom. Okay, if there's more than one central atom, you can talk about the geometry around atom number 2 and atom number 3 using the Vesper theory if you like. But here, we're only considering this one central atom in this relatively simple molecule. Okay, so you look for the central atom, and the next step in applying the Vesper theory is figure out how many regions of electron density around that central atom exist. These can be either lone pairs count once, bonding pairs count once. Okay, so as I look at this, I say, okay, well, where are my regions of electron density? I've got one region right here, this double bond, that's one region. Second region over here with this single bond, that's 2 regions. Third region is right here, this lone pair of electrons. So this has got 3 regions of electron density around that central atom. Sometimes there's 3, sometimes there's 4, sometimes it could be as many as 6. Usually, generally speaking, between 3 and 6, I guess maybe 2 in some cases, okay? But my point here is that number of regions of electron density is primarily the driving factor that allows us to predict the geometry. It's the crucial factor that allows us to predict the geometry of our molecule and ultimately our electron groups. The reason why that is the Vesper theory states that these electrons, which are involved either in bonds or lone pairs, they want to get as far apart from one another as possible. Electrons are always negatively charged. They always repel each other. So it makes sense that the bonding pairs and the lone pairs will distribute themselves in 3-dimensional space to get as far apart from one another as humanly possible. And that is what drives the electron group geometry and ultimately the molecular shape. Okay? Now, how can three regions of electron density get as far apart as possible from one another? Well, think about it if they arrange themselves in this way. Okay? Central oxygen, so the blue spheres represent oxygen here. And this little purple sphere on the top, that's going to represent my lone pair electrons. That's my purple, and each blue is my oxygens. Okay? Think about if they arrange themselves in this way. Got my lone pair of electrons here, oxygen, oxygen. Here's my double bond. Here's my single bond. A region of electron density, the bonding pairs, and the lone pairs. If they arrange themselves in this way, they're all kind of in the same plane, but just like this, the electrons get as far apart from one another as they possibly can. Turns out this is the geometry that minimizes the repulsion between the three different electron groups. Okay? So, what's the difference then between the molecular geometry and the electron group geometry? Okay? Well, the electron group geometry considers my lone pairs. Okay? It considers my non-bonding electrons. That's the electron group geometry. However, the molecular shape does not consider that. So if I want to talk about electron group geometry, which is what I really want to consider here first, I need to consider all the parts of my molecules, even my lone pairs, that purple, that's up there at the top. You see that? If I've got three regions of electron density, 1, 2, and then the lone pairs, the best way to arrange those three are in the so-called trigonal planar geometry. It makes a triangle between points 1, 2, and 3, and they're all lying in the same plane. All my dots are in the same plane here, okay? So it's trigonal planar electron group geometry. It's the most favorable energetic way to get these all as far apart from one another as possible. Trigonal planar. Now again, that geometry, the electron group geometry, I'm harping on this because it's important, right? That describes the spacing, if you will, or the geometry of my electron groups around the central atom. Remember, this is my lone pair. So I don't care if I've got bonding pairs or lone pairs. I'm describing the geometry around the central atom with respect to all groups of electrons. That's trigonal planar here. But if I want to talk about molecular shape, or the shape of molecules, the situation is different. Because if I want to talk about my molecule shape or my molecular shape, I do not consider the lone pairs. So you see I've removed that purple sphere. Do not consider the lone pairs for molecular shape, and that's the difference. So while there is a lone pair here in my Lewis dot structure, if I'm speaking or describing the shape of this molecule to someone, it's still there. It's still exerting an influence on the structure. Okay, it's not disappeared, but I only describe the shape of the molecule and its atoms. Now in this particular case, what was a trigonal planar electron group geometry has now been reduced to a bent or a V-shaped molecular geometry. So it's different now. So the moral to the story here is that if I've got three electron groups around the central atom, I may have this guy, my trigonal planar electron group geometry. This is my lone pairs, right? But if I'm talking about molecular geometry, the lone pairs are still there, and that influences the shape of the molecule. Okay, that's important to realize. You never lose the influence of the lone pairs. But if I'm describing the molecular geometry itself, it looks like it's bent or V-shaped. Okay, so this is the shape of ozone. This is what it would look like according to the Vesper theory, if you could actually see it under a microscope or something of the sort. Okay. All right. So hopefully that helps. Now, we need one more thing to consider here. What about our bond angles? Bond angles. What we're talking about when we consider bond angles is what would be the angle made between the atoms. This angle right here, down here at the bottom, okay? Between here and here. What is that angle if I was to measure it, okay? Between this point, and this point. Now, for each geometry, that bond angle is different. Because what determines the bond angle, again, is this idea that the electron pairs kind of get as far apart from one another as possible. Now, in this particular base geometry, where there are 1, 2, 3 electron groups around the central atom that form this triangle, hence the name trigonal planar, that bond angle down there at the bottom here, between here, here, and here, that bond angle, in the perfect case, is 120 degrees. Now that's the perfect bond angle, 120 degrees, between here, here, and here in ozone. Now, it turns out that in nature, these lone pair of electrons tend to take up more space than a bonding pair that are more localized between the atoms. Okay? So as a result, this lone pair would have a tendency to ever so slightly push these two a little bit closer together, and the bond angle would be a little bit less than 120. So here's 120 in the perfect trigonal planar geometry, and that lone pair taking up some more space would kind of push these two together a little bit more. So the bond angle would be slightly less than 120 in this particular molecule, okay? But nonetheless, the perfect bond angle would be 120 in this trigonal planar geometry. Okay, so that's the first case. Now let's go through a couple more. We can familiarize ourselves with this, because it's a little bit, I guess, difficult to see it at first, but once you get it, you're going to be home free, okay? Next one, H3O plus 1. It's the hydronium ion. This is water plus a proton, H plus. This ion you'll see a lot when you talk about acids and bases in the second semester of general chemistry. H3O plus 1 hydronium ion. It's believed that the acids basically donate their protons to make this hydronium ion when they're in aqueous solution. So you'll talk about this a lot in your 1308 class, right? But here we just want to predict the shape and electron group geometry of all this. So we start this by doing the same exact thing. We come up with our Lewis dot structure. It's always required to predict the shape of a molecule is your Lewis dot structure. So you go to your periodic table, you figure out how many electrons each of these bring to the table. You've got 3 copies of hydrogen. Each one is bringing 1. You've got 1 copy of oxygen, and that's going to bring with it 6. So it looks like at first glance we have 9. But we have what? An ion. It's H3O plus 1 in this case. So this ion has 1 less electron, or 1 fewer electron, than it should. So I'm going to subtract 1 so that we've got a perfect 8 or octet to use. And then we find our central atom, which is here going to be the oxygen. We arrange the other atoms around it, sort of symmetrically at first. And we go about completing our octets. In this particular case, I think that this works, right? We got 2, 4, 6, 8 electrons. The hydrogen have got their duets, which is what hydrogen requires, or what it wants, so to speak. So the hydrogen is happy, and the oxygen's also got its octet. That's 8 around the central atom, so it is also sort of happy as well, okay? So the next thing is predicting our electron group geometry. How do we predict our electron group geometry? What strategy do we use? It all goes back to that central atom, figuring out how many regions of electron density are around the central atom. I've got 1, 2, 3, 4 regions of electron density. Remember, bonding pairs count once, lone pairs count once. So 1, 2, 3, 4. If you've got a double bond or a triple bond, it only counts 1 time. So any bond only counts once. Okay? So 1, 2, 3, 4 regions of electron density. Okay? So I'm going to put that here, 4 regions of E minus density. The reason why I'm making note of that again, and I'm harping on it, is that's what drives the geometry, the number of electron regions of density around the central atom. If you figure that out, you can figure out what your geometry is. Okay, that's the step that's required. Now, whenever you have 4 regions of electron density around the central atom, you've got tetrahedral electron group geometry. That was one of our base Vesper geometries, tetrahedral. Having that tetrahedral electron group geometry is always present when you've got 4 regions of electron density around the central atom. Turns out this is one of the most common geometries that you're going to encounter. Okay, this comes up a lot in chemistry. So this tetrahedral geometry is particularly important, I suppose. Now, what does a tetrahedral geometry look like to us? So let me bring that up at my models here real fast. Okay, so this is a perfect tetrahedral geometry where there are 1, 2, 3, 4 regions of electron density around the central atom. So you can kind of see what that looks like. This, again, is the geometrical arrangement which reduces electron pair repulsions. It gets the electron pairs as far apart from each other as humanly possible when you've got 4 electron pairs. Okay, so this is the way it works. Now, notice that these white spheres are slightly lower than the black sphere, which is our central atom. Okay, so they're not in the same plane, they're slightly lower. And it turns out that for this tetrahedral geometry, the perfect bond angle is 109.5 degrees. So that's another good number to kind of commit to memory. 109.5 degrees is the perfect bond angle for our good friend, the tetrahedral geometry, when 4 electron groups geometries, or 4 electron groups are around the central atom. Okay, so that's a bit of crucial information. So we're making some progress. So it's very fair to say that we've got tetrahedral electron group geometry, and in fact, whenever you've got 4 regions of electron density around the central atom, you always got tetrahedral electron group geometry. But what about molecular geometry or molecular shape? Remember, the shape is different than the electron group geometry because the shape only considers atoms that are bonded to the central. Now, if I had a 4th bond here, there's another bond, another atom here, this would be my molecular geometry. So if you have this, if all of your regions are bonding pairs, the electron group geometry is the same as the molecular geometry. It's always the same. If all of these are bonding pairs, okay? But we don't have that here. 3 are bonding pairs. 3 of our regions are bonding pairs, but the 4th is a lone pair. So what I need to do is I need to take one of these bonding groups and remove it, unplug it here in my model, and put one of these purple lone pairs there. Okay, I'm using my purple as a lone pair. So this is just a lone pair. It is not an atom. This purple is the lone pair of electrons. The lone pairs influence the shape of the molecule. It's very important to realize that they influence the shape. They're just not another atom there. They're just a lone pair of electrons, okay, that occupy this region in space. So if I replace that bonding pair with a lone pair, now I've got a molecule that looks a little bit different than the pure tetrahedron, okay? Because remember, no atom here, just lone pair of electrons, right? So how would we describe the shape of this molecule? Well, the central atom is still a little bit above the plane of the white atoms. It seems like maybe these white ones are kind of all on the same plane. If I turn it on the side, I guess you can kind of see that if I get it just right here, right? So these guys are all on the same plane, right? So there's a plane that I can put this on my hand, and you see that center one's up above that a little bit, right? So these white ones are all on the same plane, and they form what appears to be a triangle, and then this one's up above it here in the middle. So well, it's kind of a triangle and a pyramid shape. So maybe I should call this trigonal pyramidal. Everybody see that? Triangle, pyramid, trigonal pyramidal. So sure enough, we're going to call this molecular geometry trigonal pyramidal. Now the perfect bond angle is 109.5 degrees. But just like the previous case, these lone pairs, whenever they're present, lone pairs tend to take up more space, okay, and push things away from them. So as a result, while the perfect bond angle, say, between here, here, and here, will be 109.5 degrees, in reality, the lone pair is going to kind of push these guys together just a little bit more. It's usually just a small deflection from the perfect bond angle, but it's going to push them together just a little bit more. This is going to take up more space, and the bond angle on this molecule is probably a little bit less than 109.5 degrees as a result. But the perfect bond angle is 109.5, okay? And that goes for any tetrahedral geometry. All right, moving on. So I think we got one more of these on the far right. We've got NF3. We start by drawing our Lewis dot structure. The nitrogen brings 5 electrons to the table. Each fluorine is going to bring 7. So we've got a total of 26 to work with. Okay. I'll draw my N in the center because fluorine is generally never a central atom. Bond it to my 3 fluorines. Complete my octets for my fluorines. I'm going to also guess I'm probably going to need a 2 on the central nitrogen. Let's just make sure that works out. And I forgot 2 dots right here. Okay. So 6 lone pair electrons, 12, 18, 20, and 3 bonding pairs makes 26. So I've used 26. I had 26 to use. The octets of everything are complete. That's my Lewis structure, okay? Now, go through the process yourself. What's the next thing that we assign? After your Lewis dot structure, you can assign electron group geometry. What test do you use to figure out what that is? You figure out what? How many regions of electron density are present in the Lewis dot structure around the central atom. So we've got 1, 2, 3 bonds. Each one counts once. That's 3 plus my lone pair of electrons. That makes 4. 4 regions of electron density dictate, again, we've got tetrahedral electron group geometry. Anytime there are 4 regions of electron density around the central atom, you're going to have tetrahedral geometry. That's the way this works. The number of electron groups around the central atom, or regions of electron density, the number of that determines what your electron group geometry is. Now, if you've got lone pairs, that changes your molecular geometry, right? So your base tetrahedral, just like it was before, in this case, looks like this. But here we've got 4 bonding pairs. 1, 2, 3, 4. I'm going to replace one of those again with a lone pair, just like I did in that previous example, right? So now this is my lone pair, just to give it a different color, because I have a lone pair up here, right? So isn't this geometry exactly the same as what we just considered? Isn't it also trigonal pyramidal? It's got 4 regions of electron density with 3 bonding pairs, 1 lone pair. It's trigonal pyramidal, just like that case that we considered. So hopefully you can start seeing similarities between the central atoms in both cases. Here, there are 4 total regions, 3 of which are bonding pairs. Here, 4 total regions, 3 bonding pairs. It's the same. And as a result, the geometries are the same. So the perfect bond angle there is also 109.5. It's the perfect case for a tetrahedral geometry. But the lone pairs tend to take up a little bit more space. So again, the bond angle on that particular molecule would be a little bit less than 109.5. Now, in reality, would these two have exactly the same bond angles? They would not. They'd be slightly different because the atoms that make up these 2 molecules are a slightly different size. They have different numbers of electrons, so on and so forth. So, the exact physics of the repulsion between the electric pairs would dictate that these 2 numbers are not exactly the same. Both of them would be a little bit less than 109.5. But they would vary depending on what atoms are involved, ever so slightly, okay? But nonetheless, this is kind of our introduction to predicting VSEPR geometries from Lewis dot structures, or we really started with formulas, okay? This is the process of what you need to go through. Now, the key things to keep in mind for doing this on your homework assignments or on the exams. You need to be able to write your Lewis dot structures. And then after that, you need to understand that the number of electron density regions dictate your electron group geometry. Okay, that's what dictates this. And then from that, you can predict the molecular shape. You also need to familiarize yourself. This is, in the vicinity of page 418 to maybe 425 or so of your textbook. With all of the possible geometries. There's usually a nice little table that summarizes everything. Oh, it looks like it's on page 424. There's a nice little flow chart, and then there is a diagram, figure 10.10, that shows common molecular shapes with all the different variants. You need to kind of familiarize yourself with this, even memorize it a bit. I mean, sort of sometimes you can kind of reason your way through it if you think about minimizing the repulsions between the electrons as they are around the central atom. But these geometries are sort of the base geometries that you can use to predict the shapes of molecules, and you really have to kind of know those to apply this. But again, this is a crucial skill here in Chapter 10. If you really want to do well on the test, not only do you need to be able to write these Lewis dot formulas, but also predict your Vesper geometries. This is really a crucial skill from here, this first semester part of the course. All right. So I hope this was useful.